Hello. Welcome back to CS422 Theory of Computation. And we are talking about formalizing what it means to be computable. And to this end, we have introduced the following notion, what it means to decide decision problem, what it means to semi-decide a decision problem, and what it means to enumerate a decision problem, where a decision problem in our definition is just a subset of natural numbers. And remember that by simply counting, that we saw that there are more than countably infinitely many decision problems, as opposed to at most countably infinitely many algorithms. For any reasonable notion of an algorithm, which we will going to formalize later. And we've started comparing these notions rigorously with the theorem you can see here. First item says that every finite decision problem is decidable. So that means kind of from the computability perspective, the finite ones are trivial and therefore uninteresting, and we will go to ignore them for the rest of this course. The second item says that the decidability is closed under complement. So it says if a decision problem is decidable, then also its complement is decidable and vice versa. And the third item, C, justifies why we gave in our definition the name semi-decidable. Namely, it says that a decision problem is decidable if and only if both the problem and its set theoretic complement, the set n natural numbers without the elements of L, both are semi-decidable. And thus, this is a reasonable notion calling it semi-decidable because it's really half, and both halves together to make up the original decidability. And finally, we've established the connection between enumerability and semi-decidability. And it turns out that these are almost the same as long as we're interested in infinite problems, which we are, as you recall, because the finite ones are trivial and uninteresting according to item A anyway. And also recall the subtle difference in the superficial conception between semi-deciding and enumeration. Semi-deciding receives an argument as input and is supposed to tell whether this belongs to the set or remains forever silent if it does not. Whereas so that's only input, whereas enumerating is outputting all elements of the set in an arbitrary order, not necessarily lexicographical order, and outputting here being formalized in terms of this function, total computable function, which is furthermore supposed to be injective, meaning that no element of the set is allowed to be output twice. The emphasis here is really in arbitrary order, and as you know, sorting an infinite set is a very subtle problem. We've maybe learned a lot about sorting problems and sorting algorithms in Introduction to Computation, but sorting an infinite set, that's very subtle. Even the definition of what it means is beyond the purpose of what we discussed here. So, and we've also seen proofs of these statements, and I've given informal proofs as part of the pedagogical concept of this lecture, namely offering you the opportunity to write down the proof by yourself. And in this way, this is really where the learning happens. I'll say more about the pedagogical concept in a few minutes. So let's just briefly recall that in a finite decision problem can be hard-coded kind of into an algorithm because it's finite information, and therefore the algorithm can basically decide the problem whether a given element belongs to the set L or not. And for the item B of the theorem, we kind of transformed a hypothetical algorithm that decides the set L into one that decides its complement without really going or knowing or assuming anything about the algorithm. It's the proof is kind of a black box transformation on algorithms, converting one algorithm into another. And for the third, it was a similar transformation on algorithms, only that the direction from both being semi-decidable to decidable, we had to somehow schedule the two algorithms, the one semi-deciding L and the one semi-deciding L's complement, because precisely one of the two is going to terminate and we don't know which one. So we cannot first run the first one first and then the second, because chances are that the first one does not terminate. Instead, we've employed this technique that we will use very frequently throughout the course of this lecture, which is called dovetailing, which is in a sense a simultaneous simulation of, in this case, two and later actually also even infinitely many algorithms, step by step, which is a kind of what your computer does when it pretends to be multitasking. Actually, it switches back and forth very quickly. The single processor switches back very quickly between all the programs that your computer is running, and thus gives us the impression that it is simultaneously executing all of them. And this is basically also the idea, historically even the original idea in this proof. And for the last item, we've started with a proof. So let me briefly remind you of the proof. It's an equivalence again. And so we need to prove two directions, if and only if. And the first direction is suppose that L is enumerable, meaning that there exists such an algorithm that computes this total injective function whose range exhausts precisely the set L. And the first observation is that this function is injective and the domain is infinite, therefore also the range must be infinite. That means we have indeed an infinite set at our hands. And the second part, being semi-decidable, suppose let's describe an algorithm that semi-decides this problem. So the algorithm receives as argument some input x, a natural number, and then repeatedly calculates f of 0, f of 1, f of 2, and so on. And by hypothesis, since this function is totally computable, it means that every single of these computations terminates. So here, we don't really need to worry about a kind of scheduling or interleaving or dovetailing. We really can calculate f of 0 and then look at the output and compare it to the input of our algorithm. So our algorithm uses the algorithm computing f as a subroutine to repeatedly calculate f of 0, f of 1, and for each one, compare the output on that computation with the input x that we have received. And once a coincidence occurs, that means that our input indeed belongs to the range of this function, belongs to the L, and then our algorithm, we just construct our algorithm to terminate, which is precisely the definition of semi-deciding, namely it must terminate for inputs which belong to L. Whereas if the input does not belong to L, then this execution and search, f of 1, f of 2, f of 3, and so on, continues indefinitely. It will never be a coincidence, because right now we're talking about the case where x does not belong to L. And so in this case, this means that the computation indeed carries on indefinitely, which also is this other condition of semi-deciding, namely to terminate precisely on inputs which belong to L, or put differently, it must not terminate on inputs which do not belong to L, which the algorithm we have just described satisfied. And observe that again, our proof here that enumerable implies infinite and semi-decidable proceeds by constructing a transformation on algorithms. We take the algorithm which computes F, which the hypothesis says exists, and we transform that into an algorithm which semi-decides L in the way we've just described, and then verify and confirm that our newly constructed algorithm has the required property according to the definition of semi-deciding. So that proves one direction in the equivalence here. And now for the converse direction, we're going to perform a similar modification or operation on algorithms, abstract algorithms. But let's first notice that since the set is infinite, in particular, it contains some element. So it's not empty. And this, we pick such an element here and fix it and hard code it again into the algorithm which we're going to construct, right? Finite information can be hard coded as kind of a constant in our algorithm. So now let's use the hypothesis that other hypothesis that there exists an algorithm which semi-decides this problem. Let's call that algorithm A. And we are going to convert that to construct an algorithm which computes a total function with this property. And that we're going to call, let's say, B. And this algorithm will hard code the element W, the element W in this set. And our new algorithm B will receive as input a pair. And now recall Hilbert's Hotel. So although our algorithms only can accept one natural number, using Hilbert's Hotel, we can describe the algorithm that accepts a pair as input. Namely, it receives as input a natural number, which is an encoding of two natural numbers combined. And then the algorithm will do is to recover the two parts, X and M. So when I say it receives as input this natural number, what I mean, it receives natural number, which is supposed to be a code of a pair. And then the first step, the algorithm recovers the two parts of the code. And then the algorithm we're currently constructing is going to go ahead and simulate the algorithm semi-deciding L. Namely, it's going to simulate that algorithm on the input X, the first component here, for M steps. It's another important and interesting technique that we will use frequently, namely not just a simulation, which we've done before, like in an interpreter, but simulating for a certain fixed number of steps. Simulating for a fixed number of steps, this is what allows us to guarantee that our new algorithm indeed terminates, right? If the algorithm A does not terminate, which will happen a lot since it's supposed to semi-decide only, then all simulation will not terminate. But by including this kind of instruction counter, simulate only the first M steps of the algorithm A, this ensures that also our simulation will terminate. And once it terminates, our new algorithm will look at what has happened in the simulation so far. And there are two cases: either the simulated algorithm has terminated within the first M steps, or it has not and continue beyond that, but we don't know for how long. And the algorithm we're currently constructing, algorithm B, will proceed as follows. If it has, the simulated algorithm A has terminated within M steps on input X, then our new algorithm will output X and stop. Otherwise, our new algorithm will output W and stop. Observe that in both cases, our new algorithm will output. So indeed, it will always terminate and always outputs something on any possible input. So the algorithm we just described indeed computes a total function from natural numbers to natural numbers. That's the first important property. Next property is that the algorithm we just described, the function, total function it computes, has range coinciding with the decision problem L. Why is that the case? Well, if it outputs W, then W belongs to the set by hypothesis. Recall that W is the hard-coded fixed element that we choose in advance before constructing our algorithm B. Whereas if the algorithm outputs X, that means that the simulated algorithm A has accepted X within M steps, but the importance is it has accepted and therefore terminated, which according to the definition, hypothesis that A semi-decides set L, it means that X belongs to L and therefore, since our new algorithm outputting it, also in this case, it will output an element of L. So that anything output by the function we've computed by our new algorithm indeed belongs to L. Now, the second condition here implicit in this equality is that it outputs everything that belongs to L, right? So not just everything it outputs must belong to L, which implies one inclusion set theory, but also the opposite. It exhausts L. Why is that the case? Well, consider any element in L, and then that means that the algorithm A on input of this element will terminate with a finite number of steps. We don't know how many steps, but whatever the number of steps is, that number of steps will occur as input M for some choice here. So that means there exists a pair X comma N such that to every X in L, there exists an M such that the algorithm A accepts X within M steps. We don't know which M, but it exists. And now consider this pair, which is a natural number here. So it belongs to the domain of F. And upon the input of that natural number, our new algorithm will recover X and M, will simulate A, and will detect that A does terminate within that number of steps, and therefore output X, which shows that indeed our new algorithm, the function it calculates, outputs precisely all and only elements of L. So that concludes the proof, right? So we've taken our algorithm that A that semi-decides L and converted it into an algorithm that computes a total function whose range coincides, that is exhausts, but does not exceed the decision problem L. End of the proof, right? End of proof. No, there's something missing. There's a mistake in the proof. What is the mistake? What is the gap? The function computed by our new algorithm B is not going to be injective. If some input X makes the algorithm A terminate within M steps, then the same X will also make the algorithm A terminate within M plus 1 steps. So on input X comma M combined into one natural number, our algorithm will output X. And on input X comma M plus 1, our newly constructed algorithm will also output the same X. So two different inputs lead to the same output X, which is a violation of injectivity. Here's it. So what are we going to do? Well, we need to fix, we need to mend, to repair our proof. We need to repair our algorithm. Namely, what we're going to do is we describe a second algorithm, which kind of takes as input the previous first output of the first algorithm, the function calculated here, which is total and has this range, but it's not injective, and we convert that into an algorithm which computes another total function with same range, but now another function is to be injective. How do we do that? Well, we take our next algorithm, that's called that C. It's already our third algorithm. And that algorithm C will simulate the algorithm B, which we just described, algorithm B computing this function, which is not injective. And it will compute that function f of 0, f of 1, and so on, and record all outputs of that algorithm and store them in some internal database I'm not going to formalize how that works. Let's say some array, some infinite array or whatever, some infinite list. But the point is, our new algorithm C will check for every new element to be added to that list, for every new output computed by f of 0, f of 1, and so on, whether it already is contained in the list. If it's not, then our new algorithm C will simply output that element because it's new. It does not violate injectivity. Whereas if it is already contained in the list, then our new algorithm C will simply quell that, discard it, and proceed to f of the next element, hoping that this is new, and so on. In this way, our new algorithm C will output an enumeration of the same range as our previous algorithm B, but since our algorithm C is quelling, is suppressing any repeated output, our new algorithm C will satisfy the injectivity. And since by hypothesis the set is infinite, our new algorithm C will indeed also continue to output more and more elements. So when there's a repeated element, it will be quelled. It will try the next one. If that's also occurred before, it will also be suppressed, and so on. But since the set is infinite, eventually a new element will occur and will be output, so that indeed our new algorithm C again calculates a total function which we have just prepared to satisfy injectivity. So that concludes the proof of item D of our theorem. Indeed, enumerability, which means output, 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 is the same as infinite, and semi-decidable, which means input and either answer yes or not answer at all. And you may have noticed that in our proof, the way we've presented it, we've become less and less formal, right? So we've described, this is not even pseudocode. This is a very vague description of an algorithm, which is fits kind of our stage in the lecture where we have not yet fully formalized the notion of an algorithm. But you can easily implement that and conceive that this is possible in your favorite programming language like Python, Java, or whatever. Here we can become even more informal. Namely, we've described how to convert our algorithm B, which computes a total function with this range, into an algorithm C, which computes a total injective function with the same range. And I've refrained from even writing down any notes regarding that. And the reason for that is due to pedagogical. Right, before I get to the pedagogical perspective, there's a great question, an excellent question actually in the chat. Thank you so much. The question is, how do we choose W? How do we choose W? And this is a great question because it allows me to expand on a very subtle aspect of computability theory. So when we're asked to prove that something is computable, that means we're supposed to describe an algorithm and then make sure that this algorithm is correct and performs the way it does. With we, I mean we as scientists, as mathematicians. It's not that some algorithm is required to produce that algorithm. It's we. And therefore, we can argue in this indeed very subtle and non-constructive way. So constructive mathematician would reject that proof because it doesn't say how to choose W from L. But we as classical mathematicians, by the hypothesis that L is not empty, we know that such L exists and we're going to pick it and we're going to hard code it into the algorithm because we're supposed to show that there exists such an algorithm. And to illustrate that, or to drive that point even further home, consider the decision problem of whether God exists in your favorite religion. This seems to be a very hard decision problem, right? But this decision problem is decidable. Why is it decidable? To show that the decision problem of whether God exists or not, to show that this is decidable, we just need to describe an algorithm which decides this problem. And to show that such an algorithm exists, consider actually two algorithms. The first algorithm that just outputs yes, regardless of what the input, just output yes and stop. And the second algorithm will just output no and stop, regardless of the input. One of the two algorithms will be the correct one to answer the question whether God exists or not. So we have thus proven that this decision problem is decidable. And you already see the subtlety driven to a joke, kind of, because of course the question is, for practical purposes, which of the two algorithms is the right one? But in computability theory, this question is not addressed. We just need to show that there exists an algorithm which answers the problem, and we have constructed such an algorithm. And similarly, here, we just need to show that there exists an algorithm which enumerates this set, and that's what we've done. We didn't really describe how to find that algorithm. We just proved that it exists. I've become less and less formal in our proofs. And the reason for that is I want to prevent you from memoizing our proofs. Instead, the goal of this lecture is that you get to understand the proofs, the constructions. And the best way to do that is by forcing you to give your own proof. Maybe following along the lines of what I describe in words in this recording, or maybe you find a different proof, but the essence is learning by doing, and that means you are supposed to do it. So, and why do we prevent, or why do I want to avoid you from memoizing? Because according to Bloom's taxonomy of cognitive learning, knowledge is the lowest level of learning, which is not to dismiss the importance of knowledge, but I'm sure that you have learned how to accumulate, how to amass knowledge throughout your elementary, middle, high school, and undergraduate studies. So it's now time to move on, to force you to move on to higher levels of cognitive learning. That means comprehension, application, and analysis, maybe even synthesis when you try to find your own proof. And that becomes increasingly important in the age of internet, where anything that amounts to knowledge can easily be looked up in the internet. And thus it becomes less and less important to be able to have facts memoized. So please bear with me for your own benefit, and use the opportunity to recap the lecture after each session. Try to write down your own proof, formally or informally, based on maybe what I've described merely in words, on purpose pedagogically. Thank you. And that being said, let's now move on to the next slide, which is about comparing decision problems. Comparing decision problems in a formal way that allows us to actually create a hierarchy and realize that there's a hierarchy among the undecidable problems. Right? So superficially, there's only decidable and undecidable problems, and we've already seen examples of undecidable problems. But it turns out that there's a hierarchy. There's even more undecidable and so on. And this hierarchy actually resembles in many ways the hierarchy of infinite sets that you may know from mathematics, right? Superficially, there are only two kinds of sets, finite ones and infinite ones. But as Cantor demonstrated, among the infinite ones, there's again a hierarchy of more and more infinite. For example, the set of natural numbers is as infinite as the set of prime numbers, as infinite as the set of even numbers. However, the set of real numbers is even more infinite than the set of natural numbers. The set of subset of natural numbers is as infinite as the set of real numbers, but not countably enumerable. And one can continue that and construct an entire hierarchy of more and more infinite sets. And what we will discover is that the same holds true for decision problems. But to this end, we need to be able to compare decision problems in a similar way that we need to be able to compare different magnitudes of sets. And sets are usually compared with respect to injective or surjective mappings. So if this set is at least as large as this set, if there exists an injective mapping from this set to this set, or equivalently, if there's a surjective mapping from this set to this set. So by means of injective or alternatively equivalently surjective functions, either from here to here or from here to here, that's a way to compare how infinite different sets are. And we need, and we're going to introduce a similar way of formalizing the notion of comparing how undecidable problems are. And this is the subject of this slide. And to recall and to provide some examples, recall that here we have the halting problem, which we've already seen to be undecidable. Here now, already a little bit more formal as a set of natural numbers. Recall our notions of deciding, semi-deciding, and enumerating pertain to subsets of natural numbers. And previously, the halting problem was just informally the question of whether a pair given algorithm A and input X, whether A on input X terminates. This is our terminology of A on input X. And now this has, we formalize this as a subset of natural numbers, namely an algorithm is or will be formalized as a natural number. For now, imagining this to be the natural number represented by the binary encoding of your favorite programming language. X is a natural number anyway, all inputs are natural numbers. And using Hilbert's pairing function, we combine that into another natural number. So now here it's a natural number. So, and this is a set of natural numbers, namely all those pairs for which it terminates belong to H by the very definition. If it does not terminate, then it does not belong to H, which is in agreement with our definition of semi-deciding. So to summarize, this formalization of the halting problem as a subset of natural numbers is semi-decidable in the sense that we've just introduced, but it is not decidable in the sense that we have just formalized, because that was our proof of the very, very first session of the introduction and motivation. We know it is not decidable, but it's semi-decidable. And the second example that we want to consider is the non-triviality problem. Namely the question, here the input is only one algorithm, no input. And the question is, does there exist an input on which this algorithm terminates? Why is this called non-triviality? Because if there does not exist such an input, then the algorithm is kind of trivial, useless. It never terminates on any input. There's nothing useful to be gained from such an algorithm. Whereas an algorithm which terminates on some inputs and does not terminate on other could at least be useful for those inputs on which it does terminate, right? So that's a non-triviality problem. And the first question is, How difficult is that? Is that decidable? Is that semi-decidable, more or less than the halting problem? And we're going to answer that question using a formalization that will appear in the bottom of this slide. But first, let's introduce a third example problem, the totality problem. Totality problem is again a problem, decision problem, which only pertains to one algorithm as input, and it asks whether this algorithm terminates on all possible inputs. Now, these are the most useful algorithms, right? Those which terminate on all possible inputs. Those algorithms which terminate on some and not on others are maybe less useful. And those which never terminate are the trivial ones. These are entirely useless. And the question we ask here is, how difficult are these problems in terms of their semi-decidability and decidability? So it means we want to compare the problems. And to this end, let's introduce the following notion. For two decision problems for two subsets of natural number, we write L is less or equal to L prime. And the intuitive meaning that we want to capture formally is that L is at least as hard as L prime. If there exists, around here you see a depiction, formal depiction of these two decision problems. Here's L, here's L prime. These are both set of natural numbers. The big blue rectangles indicate the set of natural numbers. And outside of this set L, there's a complement of L. And here outside of the set L prime, there's a complement of L prime. Now, how can we compare these two decision problems? We compare by demanding that there exists a total computable function from this blue blocks to this blue blocks, from natural numbers to natural numbers, with a property that it maps the positive answers to the first decision problem, namely those x that belong to L, maps that to positive answers to the second decision problem, namely f of x must then belong to the second decision problem, and vice versa. Maybe this should be an equivalence. The negative answers to the first decision problem, elements of L complement, are to be mapped to the negative answers to the second decision problems, to elements that do not belong to L prime. Right. And why is that a reasonable way of formalizing that L is at most as difficult as L prime? Because, yeah, here's a depiction of such a function. So it must map the elements which belong to L to elements which belong to L prime, like here. The function is not required to be injective. Here you see that here are two different elements in L that are mapped to the same element of L prime. Elements that do not belong to L, like here, are to be mapped to elements which do not belong to L prime, like here. And again, injectivity may be violated. Also, we don't require surjectivity. So it is well permitted that this function misses some elements of L prime and that it misses some element of L prime complement. So no injectivity nor surjectivity, but it must be a total function, must be computable, and it must map elements from L to elements in L prime, and it must elements from L complement to elements from L prime complement. So this is our definition. And why is that a good definition? Why does that capture the intuition that L is at most as difficult as L prime computationally? Because if L prime is decidable or semi-decidable, then it follows that also L is decidable or semi-decidable. This is what we expect from such a relation, that it respects decidability and that it respects semi-decidability. So let's prove that statement. Let's prove that. So by hypothesis, there exists an algorithm which let's say, semi-decides. Now let's start with decides. There exists an algorithm which decides L prime. Also, hypothesis, there exists a computable function with this property, which means there exists another algorithm. Let's call the first algorithm A and the second algorithm B. B computes the function, A decides L prime. How can we construct from that an algorithm that decides L? Our new algorithm, let's call it C, will receive as input some natural number X, will then invoke the algorithm B, computing the function F, in order to arrive at f of X. Let's call that Y. F of X. And that subroutine call will terminate because the algorithm A is supposed to compute a total function. Now, what about Y? According to the condition here, Y, which is short for f of X, belongs to L prime if and only if X belongs to L. So our algorithm C now takes that output Y of algorithm B and feeds that into the algorithm A, which by our hypothesis decides L prime, and thus gives the correct answer whether Y belongs to L prime or not. And according to this definition, it means that this answer is also the correct answer of whether the original input X did belong to L or not. So this proves that whenever L prime is decidable, and whenever L is less or equal in this relation to L prime, then also L is decidable because we've just constructed an algorithm deciding L from the two algorithms, the one deciding L prime and the algorithm computing this total function. And I leave it to you as a very recommended exercise to repeat the same proof for semi-decidability. So this justifies this notion, namely if L prime is decidable, then also L is decidable. So in a sense, L cannot be more difficult than L prime. But the benefit is that this definition also applies in case that L is not decidable or semi-decidable, and thus allows us to compare different decision problems regardless of whether they are decidable or not, and in particular to compare undecidable decision problems, which will give rise to this hierarchy. But first, let's record another important property of the relation we've just introduced. It's always very important when making a decision to double check, to make some sanity checks that this is a reasonable definition. And the next sanity check we want from such a definition, it should be kind of like a order relation, right? So it should be almost an order relation, and the important property of an order relation is transitivity. So indeed, this notion satisfies transitivity if L is at most as difficult as L prime, and if L prime is at most as difficult as L double prime, then we would expect L to be at most as difficult as the L double prime if this definition accurately captures our intuition, and indeed it does. So let's prove this second property, transitivity. So that means there exists a computable function that translates the positive answers of decision instances of L to positive instances of L prime. And then there exists another total computable function, let's call it G, that translates positive instances of L prime to positive instances of L double prime. F here, G here. And now I leave it to you to verify that the composition, first F, then G, or put differently, G after F, that this composition indeed satisfies this property, namely reduces from L to L double prime. This is easy. And the second, also easy observation is that this composition is again computable. Maybe we take the algorithm which computes F and take the output of that computation and feed into the algorithm that computes G. And thus the composition of the two algorithms, the one computing F with the one computing G, is the new algorithm computing the composition G after F. And observe that again, here we have played our game of operating on abstract algorithms, the algorithm computing F, the algorithm computing G, combined to an algorithm computing the composition without any hypothesis of how the algorithm computing F or the algorithm computing G really works internally, just combining them together. So that proves the two important properties of this notion of reduction. And just for those of you who may have already some background in complexity theory, who may know the notion of polynomial time reduction. Indeed, this historically was the precursor. This is the resource unbounded, the non-complexity theoretical, the just computable version of a reduction, which historically preceded the polynomial time refined version introduced by Stephen Cook, whereas the mere computable reduction, the qualitative notion of reduction, dates back to Alfred Tarski. Okay, and now having thus introduced these notions, we can have a look at the three example problems and try to compare them, right? But before that, yes, there's a great question in the chat. What is a computable function? That's a great question because it allows me to return to a previous slide where we defined what it means to be a computable function. We defined what it means to be a computable partial function. But since the function here is total, the partial part in the definition is not really relevant. So it really means that there exists an algorithm which on input X outputs f of X and stops then. That's the definition of what it means, what is a computable function. And admittedly, I still owe you, and I will provide the formal definition of what it is, what an algorithm is. We'll do that. One particular purpose of this course is to avoid Turing machines, computability and complexity theory without Turing machines. So it fully suffices if you think of algorithm to mean a program in your favorite programming language like Python or Java or whatever. Thanks for that question. And I hope that clarifies what a computable function is. For details, refer to the previous recording of the previous lecture. Okay. Yes, and F, another great question. No, we don't require F to be injective here. In the previous notion of the enumeration, we did require F to be injective, but here F is not supposed to be, not required to be injective, nor surjective. Okay, and that being said, now let's move on to compare the above three decision problems. And the first statement we want to make is that the halting problem is reducible, computable, reducible in this sense, to the non-triviality problem. So in this sense, the halting problem is at most as difficult as the non-triviality problem. And according to item A, that means, oh, there's an addition here to item A, namely the same applies to the complement. Okay, let me revert to that. What we did prove is if L prime is semi-decidable or decidable, then so is L. But the same also applies to the complement. If L prime's complement is decidable or semi-decidable, then it follows from this reduction that also L's complement is decidable, semi-decidable, and we'll use that in a minute. Okay, but we've stated the first comparison, and it follows from this comparison that the non-triviality problem must also be undecidable. Why? Well, because if n were decidable, then according to item A, it would follow that also H is decidable, which we know from the very first lecture that it is not. So thus we have already established a second undecidable problem. Well, as established, except for that I need to convince you of this reduction. So let's do that. How can we, the intuition is, how can we computably convert? This is the intuition of this function, a computable conversion. How can we computably convert instances of the halting problem into instances of the non-triviality problem that respect yes and no answers to the two problems? And to see this, let's consider a typical instance, a typical input to the halting problem that is such a pair encoding into one natural number as using a Hilbert pairing function. And let's convert it into a new algorithm that we call that new algorithm Bx. So here we have A, and the new algorithm, which I'm going to write here, is going to have B as hard-coded, right? Remember our technique of hard-coding something. So our new algorithm B will have X hard-coded, and it will simply simulate A, the previous algorithm, on input X. So algorithm Bx will in turn receive some input. Let's call that Y. But we construct Bx to ignore its own input. That is possible in any reasonable programming language. And instead simulate in both the algorithm A, which is hard-coded in the algorithm B, on the input X, which is also hard-coded on the in the algorithm B. And now let's check the behavior of this new algorithm Bx. If the algorithm A on input X terminates, then the algorithm Bx will terminate on any input, on every input, because it ignores its input and just simulates algorithm A on the fixed input X. Whereas if the algorithm A on the input X does not terminate, then the new algorithm Bx will not terminate on any input, because recall that it ignores its input, right? That's a subtle point here. And so since it ignores its input, that means if the algorithm A on input X terminates, then the algorithm B will terminate on all inputs. If algorithm A on input X does not terminate, then the new algorithm B will never terminate on any input and therefore be a trivial one. So that now we have described informally our translation function, a function which translates positive inputs to the halting problem, algorithm A on input X terminates, to a new instance of the non-triviality problem, algorithm Bx terminates always on every input, and most importantly, negative instances of the halting problem, algorithm A on input X does not terminate, to a negative instance of the non-triviality problem, the algorithm B does not terminate on any input, which by contraposition is exactly the negation here. What remains that means we've just established this equivalence for the function we've just informally described, and it remains to assert that this function is computable. Why is this function computable? Well, the function receives as input an encoding of an algorithm A and an encoding of an input X for A, and it outputs an algorithm B which ignores its input and has algorithm A and algorithm X hard-coded. And this transformation on source codes of algorithms is easy to implement in any of your favorite programming language. So I'm going to leave it to you to describe it more or less formally. So that concludes our first proof of reduction, again, deliberately, informally, with lots of words, thus to encourage you to write it down more formally and maybe even in your favorite programming language to realize that this is indeed computable transformation on source code of algorithms. Now moving on to the next statement. Where is it? The halting problem is also reducible, computably reducible to the totality problem. Why is that the case? The proof is basically the same. We can use the same translation function, convert the same algorithm A on input X as input to the new algorithm BX, which ignores its input Y and just simulates algorithm A on input X. For the same reason, if algorithm A on input X terminates, then the new algorithm will terminate on all inputs because it ignores its inputs. Whereas if the algorithm A on input X does not terminate, then the new algorithm BX terminates on no input. So again, we have a translation that converts positive instances to positive instances now on the totality problem, and negative instances of the halting problem to negative instances of the totality problem. In particular, also the totality problem is undecidable. Moving on, the next statement is about comparing the opposite, the non-triviality problem with the halting problem. And this reduction also holds, which basically means that the halting problem and the non-triviality problem are equally undecidable, right? So here, this reduced to n, and n is reducible back to h. So that means also that this relation that we've introduced is not an order relation because it violates antisymmetry. Antisymmetry requires if h is less or equal to n and n is less or equal to h, then both are equal. They are not equal, but they are equivalent with respect to this reduction. Now, how does that reduction work? The reduction is basically modification of this dovetailing argument. So for this reduction, we receive as input just an algorithm A, right? That's an instance of the non-triviality problem. And we wonder whether this algorithm terminates on any possible input, whether there exists an input. And now we're going to do the following. We're going to put that algorithm, convert that into an algorithm that tries all possible inputs Y. So an algorithm, let's call this B, that invokes algorithm A on input Y and on input M, and simulates the algorithm A on input Y for M steps. And we see whether this algorithm terminates on input Y for any number of steps. And then we can see that this new search algorithm kind of searches for an input on which it terminates, and thus gives a positive instance of the halting problem if it and only if it was a positive instance of the non-triviality problem. So I'll leave details for you as an exercise to figure out. Let's, in view of time, move on to the second statement, namely a non-reduction. This is something new, right? So I said one of the core benefits of science is that one can prove that something is impossible. So we've proven that something is possible. And interestingly, all this possible, and it is reducible, h is reducible to n, h is reducible to t, n is reducible to a. H gave us a conclusion of impossibility. N is also undecidable. T is also undecidable. Here, a new negative kind of statement, impossibility statement, H cannot be reduced to its own complement. Now, why is that the case? Because of this item A. and because of transitivity. So recall that suppose for contradiction that A is reducible computably to its complement, then by item A, also H complement is reducible to H. And therefore the two are equivalent. And therefore by item A, that means either both are decidable, both are semi-decidable, or none of them are decidable, none of them are semi-decidable. And from that it follows that the complement of the halting problem is not semi-decidable. That was a great question in the Slack, which I really want to spend some time on. But let's first conclude this slide on. Okay. Let's go to the screen sharing. Let's share the screen again. Right, here we are. Okay, so the last statement on this slide is that the complement of the halting problem is reducible to the totality problem. And we're going to prove that in a minute, but first observe that from this it follows that also the totality problem is not reducible to the halting problem, because if it were, then that would mean that the complement of the halting problem reducible to T, T reducible to H, which is a contradiction to here. So another impossibility proof now exploiting the transitivity. So that means that the totality problem is strictly more difficult than the halting problem, whereas the non-triviality problem is as undecidable as a halting problem. The totality problem is strictly more undecidable, which already gives indication of the hierarchy that I mentioned. And later we will actually climb up this hierarchy far beyond. But so far we have on the bottom, the class of decidable problems. Then we have the class of undecidable problems that are equivalent to the halting problem, which includes the non-triviality problem. And beyond that, we have the totality problem, which is more undecidable, which defines its own class, and leave it to later stages in this course to discover even more higher degrees of undecidability. So I still owe you the proof that the complement of the halting problem is reducible to the totality problem. But first, I'd like to catch up on the question in the chat, namely example of undecidable and not semi-decidable problems. So let me briefly revert to the previous slide. Indeed, right, we had this example that the halting problem is not decidable. And we saw that it is semi-decidable, namely an interpreter that counts the number of steps it simulates the algorithm is a semi-decision procedure. But to answer the question was for a problem which is not semi-decidable, not even semi-decidable. And indeed, the complement of the halting problem is such a problem. And that follows from item C of the theorem. Let me say that again. Let's suppose that the complement of the halting problem is semi-decidable. We know that the halting problem itself is semi-decidable. If also the complement is semi-decidable, then according to item C, it means that the halting problem must be decidable, which we know it's not. And therefore, we conclude that the complement of the halting problem is not even semi-decidable, thus answering another very great question in the chat. And now, concluding this slide. So we've introduced a way of formally comparing decision problems with their degree of undecidability. We've applied this and thus achieved being able to compare these three decision problems, asserting that the halting and the non-triviality problem are both equivalent or equally undecidable, both are semi-decidable, none are decidable, whereas the totality problem is even one stage higher. In particular, it's not even semi-decidable. So that's all for today. Thank you very much for your attention. And I'm now going to stop sharing the slides and be available for your questions during the last 5 minutes of the lecture time. Thank you.